Hey guys, welcome back to another lesson. Previously we trained our model on the MNIST dataset, and it seemed to reach a reasonable loss in accuracy. A true testament to its performance would be to see if the model can take what it has learned and generalize itself to new data. We obtain our validation set by copying and pasting the following. But this time we will set train is equal to false. So as to denote that we're not using the training set, we are going to be using the validation dataset. Let's just rename this variable to validation dataset, and everything else should remain the same. This validation dataset contains images just like the training sets, although generally the sample size is significantly smaller. It tends to be 20% the size of the training data, as we will use it mainly for testing purposes. And now, similar to why we declared a training loader, we define a validation loader. Val loader, or let's just name the whole thing, a validation loader is equal to torch.utils.data.data loader, and the first argument will be the validation dataset. The batch size will remain 100, and we will set shuffle is equal to false this time, and that is because we will not be training our validation data, therefore there is no need, well, we will not be training our model based on the validation data, so there is no need to shuffle it. It is only for testing purposes. To analyze the validation loss and accuracy at every epoch, we will set val running loss history is equal to an empty list, and val running loss corrects is also equal to an empty list. And we validate the model within the same epoch. After we finished iterating through the entire training set to train our data, we now iterate through our entire validation set to test our data. We will first measure for two things: the performance of our model, i.e. how many correct classifications our model makes on the test set, on the validation set, to check for overfitting. So where we declared our training loss and running corrects, we similarly declare a validation loss and validation corrects. So we will set val, let's do it all in one go, val running loss is equal to 0, and val running corrects is also equal to 0. All right, and having done so, we can now loop through our test data. So right after the else statement, we can write for val inputs, val labels, notice how similar it is, in validation loader. And what we'll do is actually copy these 4 lines of code, where we make predictions and calculate the loss for the training images. I guess 3 lines of code, I should say. And fix the indentation appropriately. We do not want to make the same mistake as before. And now instead, we want to make predictions and calculate the loss for the test images. So we just have to change the appropriate variables accordingly. Val inputs, val inputs, val inputs.shape, model val inputs, loss is equal to criterion. And let's call this val outputs rather than outputs itself. And val loss. Okay. Val outputs. And since we are not training the neural network in this block, we do not need to call 0grad, loss.backward, or any of that. And you know what? On that topic, since we do not need to compute the derivative anymore here, so in this scope of operations, to save memory, we can write with torch.nograd. And what that's going to do, placing that in the intended scope, and what that's going to do is temporarily set all the requires grad flags to be false, subsequently invoking this block of code as a pair. That was really the only difference, similar to how one would calculate the training loss and training accuracy. We do the same thing for validation loss and accuracy, by copying and pasting the following: running corrects as well as preds. We will copy that, and we must place in the appropriate variables. Instead of outputs, we put val outputs. Running loss will be the val running loss. Val running corrects. We compare the predictions. Let's call this val preds, and val preds here as well. This is val labels. Rather than loss.item, we specify the val loss.item. And aside from that, it seems like we have everything good to go. Ideally, one would have made this into a function and call the function accordingly, but for our purposes, this will work just fine. Simply make sure to remove any training variables and replace it with the appropriate validation variable, as the process is the same. Alright, and now to calculate the validation epoch loss, it is the exact same as how we calculated the training epoch loss, where we divide the total running loss by the length of the dataset. So what we're going to do is just copy the following: epoch loss as well as epoch accuracy, after we do all the appending, fixing the margins. And we're going to call this val epoch loss will equal the val running loss divided by the length of the validation loader. Alright, and we will specify val epoch accuracy is equal to val running corrects dot float divided by the length of the validation loader. And similarly, every validation epoch loss we must append into the validation running loss history by writing val running loss history dot append val epoch loss, and we do that at every epoch. Looking back, I forgot an L here. Now we set val running loss corrects dot append, and we will append the val epoch accuracy. Recall we use these history lists to plot them on matplotlib and obtain a visual of our results. Finally, we wish to print the validation loss and accuracy at every epoch. Copying and pasting the following statement, we will print validation loss, validation accuracy, dot format. The placeholder will be val epoch loss and val epoch accuracy. Alright, so all we've done so far is calculated the validation loss at every epoch as well as the validation accuracy, simply to see how well the model generalizes itself to new data. And looking back at this, this is not a very fitting name of val running loss corrects. It does not accurately describe its functionality. Instead, we will call it val running corrects history. Val running corrects history over here as well. And everything else seems to be pretty good. We should be good to run our model, except before doing so, what I want to do is print the epoch that we're currently at. Epoch will equal the epoch E that we're currently at, E plus 1. The reason I add 1 is because E starts at 0 and we want to start at epoch 1, but without further ado, we should be good to go to start training our neural network. I will see you in a bit. Alright guys, welcome back. Right away we notice that the model is indeed effectively generalizing itself on this new data, as the validation loss continuously decreases throughout every epoch, and the accuracy also converges to 96%. This is really, really good, meaning it predicts 96% of the test images correctly. This is a really good sign of a well-working model. To further analyze the behavior of this model, we can start by plotting it on a graph. We do this with plt.plot. We will plot the val running loss history, and we'll give it a label equal to validation loss, and we'll add a legend, plt.legend, to distinguish between the training loss and validation loss. Outputting the graph, the results we obtain are very promising. It seems that during the full 10 epochs, the validation loss is seemingly smaller than the training loss. This is consistent with what we should expect. The first reason being that the training set has many hard cases to learn, whereas the validation set is then applied to a model that's already been trained, and thus has easier cases to predict. But what's really important is that the more epochs we run, the training and validation loss, they start to approach one another, until at one point our training loss becomes less than the validation loss. And that's when you begin to overfit the model, since what that implies is our model is memorizing the training set, but then it starts to fail to generalize itself to new data on the validation. So really, the number of epochs you train your model on, or even the number of hidden layers, the number of nodes in these hidden layers, the learning rates, it's something you have to be careful so as to not overfit your model, or in some cases underfit it. If I were to run this for more epochs, you can try it for yourself, but you should see the following pattern, where the validation error becomes higher than your training error, which means it starts doing a good job training itself on the training data, but performs much worse on the validation sets, as it starts to memorize idiosyncratic features with such a high capacity that the model may overfit. Given the tests that we've run, however, we could add a dropout layer, but that's a topic we'll cover later on. For the purposes of this project, our model performs relatively well. It would pose a serious problem if you were to encounter such extreme cases of overfitting, in which case one must significantly tune their hyperparameters and introduce some new regularization techniques in cases where the validation loss is significantly higher, but our model seems to be performing very well. We can plot the accuracy in much the same way, and we do this with plt.plots val running corrects history, and we're going to set that label equal to validation accuracy. And once again, we add a legend with plt.legend, and doing so, analogous to the training loss, the validation accuracy shows that the model is effectively making accurate predictions. You've just trained a neural network to effectively classify between various handwritten images. In the next video, we will further test our model by grabbing images from the web and testing them. See you in there.